Okay, good morning, everyone. All right, so we're going to start our class today. So first off, I want to make an announcement. Okay, this is actually week 12 right now. Okay, so officially our class is supposed to let me see. Okay, so officially our class is supposed to end this week. Okay, but of course we actually missed a lot of classes because of this lockdown situation. Right, we basically missed at least 4 lectures in this class. Okay, so therefore there's actually a lot of content which I haven't covered yet in the class. Okay, so if we have to end the class this week, then we're going to end up missing a lot of the important parts of this class. So what I would like to do is to extend the class for 2 more weeks. Okay, so instead of ending this week, I want to end the class in week 14. Okay, is that okay with you guys? Is that going to cause a big problem for any of you to end the class 2 weeks later?
Class 2 weeks later. Okay.
Yeah. Do you want to say something? Hopefully this is not going to cause a big problem for you guys, right? Because we actually missed 4 lectures. So all I want to do is just to make up the lectures that we missed. Okay, is that okay? Okay, what about the project? Okay, yeah, so I'll talk about the other things. Okay, but first of all, for the class, if we extend it for 2 weeks, it's okay with you guys, right? Yeah. All right. And then in terms of I know this is like a very stressful situation for all of you guys. Okay, because it's the same for me. Okay. So therefore I want to take this and these online classes. They're not a very good way to learn, right? So anyways, I want to take this stuff into account when I do the grading for this course. Okay. So then basically what I'm gonna do is so for the project. I'm going to give you guys until after the final exam. So we're going to have our final exam in like week 17 or something like that. Okay. So I'm going to give you at least until week 17 to do the project. Okay. And then also for the final exam, I'm going to try to make that be weighted towards the first half of the course where we actually had more normal lectures. Okay. So basically it's going to focus on stuff probably up to NP. Okay, so it's going to cover some things about randomized algorithms and other topics, which I'll talk about later. Okay, but the focus is going to be on the sort of first half of the course when we had more regular classes. Okay, and that's just because I know that these online classes are not the best way for you guys to learn about these things. Okay, so yeah, I'll try to take all that stuff into account. Okay, yeah. So if you have any problems with extending the course or other types of issues, you can send me an email or something like that. Okay. All right. I'm gonna mute. So I think somebody has their microphone on, so I'm gonna actually mute you guys. Okay. I mean, if you have anything to say, then by all means. But otherwise, I'm just gonna yeah, I'm gonna mute you guys. Okay. All right, so that's the announcement. Okay, yeah. So we're gonna keep. After this week, we're gonna have 2 more weeks of lectures. So that will basically allow us to finish up all the material that we were supposed to cover. Okay. Even then, I think we're gonna end up missing a bit of material because these classes are shorter than usual. Okay, but at least we'll cover most of the material. Right. Okay, all right, so then let's get back to this lecture. So last time we were talking about these things called Chernoff bounds, right? And Chernoff bounds are basically a mathematical technique to analyze, which is often used to analyze the complexity of randomized algorithms. Okay, so to recall the Chernoff bound, what we have is that we have a set of random variables. Okay, we assume that all of these random variables are independent from each other. Okay. And furthermore, their values are either 0 or 1. And the values are, the ith random variable is going to be 1 with probability pi. Okay, and now, so the expectation, so now we're going to look at the sum of all of these random variables. And the expectation of the sum is simply the sum of all of these pi's. Right? And so the Chernoff bound just gives us a bound on the probability that the sum deviates from its expectation. Okay. So the probability that the sum is going to be a factor of 1 plus delta larger than the expectation. Okay. This is going to be exponentially small in both the expectation, the mu, and also the delta term, right? The amount of deviation. Okay. Yeah, so we had several forms for the Chernoff bound, depending on like which which parameter settings we have. Okay, but basically they're all saying that it is very unlikely that the sum of many random variables, if they're independent, right, it's very unlikely that they deviate substantially from their expectation. Okay, so then now let's look at some applications of this Chernoff bound. Okay. All right, so the first application is going to be, let's consider a simple situation where you flip coins. Okay, so we assume that you have fair coins, and let's say that you flip the coin n times. Okay, so therefore you expect to get n over 2 heads. Okay, and now let's use the Chernoff bound to bound the probability that you get a lot more than n over 2 heads. Okay, so what is the probability that you get at least n over 2 plus delta heads for some given delta? Okay. Now, first of all, this is a situation where we can apply the Chernoff bound because the value that we're looking at, x, okay, this is a sum of a bunch of independent random variables, right? Each coin flip is a random variable, right? It's either 0 or 1, right? It's either heads or tails. And then all the flips are independent from each other. And we're looking at the total number of heads that we get. So we're looking at the sum of all of these independent variables, random variables. Yeah. Okay. So then, so therefore, we can apply the Chernoff bound. Okay. And now, when you apply the Chernoff bound, it's good to choose which form of the Chernoff bound to apply. Okay, because we have several forms, and some of them are easier to use in certain situations. Okay. So the form that we're going to use is going to be the form from part 1 of theorem 1. Okay. So just to go back to that. Oops. Okay, yeah, so we're going to use this form of the Chernoff bound. Okay, yeah, so therefore we basically have to take this formula and plug it into our problem. And also notice that the Chernoff bound is multiplicative. Okay, it's talking about multiplicative deviation, meaning that you're looking at the expectation and you're saying, what's the probability I get more than 1 plus delta factor away from the expectation? Right. So it's not an additive deviation. It's a multiplicative deviation. Okay. So therefore, if you're looking at what's the probability I get more than n over 2 plus delta heads, you first of all need to convert that to a multiplicative deviation. Okay. So if you get more than n over 2 plus delta heads, then that means that you are exceeding your expectation, which is n over 2, right? This mu here is n over 2. You're exceeding this by a factor of 1 plus delta divided by mu. Okay? Right, so therefore this thing, the delta divided by mu, right, this is, sorry, not delta, you're exceeding by lambda divided by mu. Okay? And this lambda divided by mu is our factor delta that you have in the Chernoff bound. Okay? All right, so then now we can plug it into part 1 of theorem 1, and then and when you do that, what you have over here is this. So we know that delta in our case is going to be lambda divided by mu, right? So the bound says that the probability is no more than e to the delta squared over 3 times mu. Okay, that's what the bound says. Okay, yeah. So therefore, we plug things in over here, and yeah, and then we get that this is the probability that we deviate by more than delta. Okay. All right, so now let's try different values of delta, and let's see how large this probability actually is. Okay, because this is a function of delta, right? So we expect that the larger delta is, the smaller this probability is going to be. Okay. So first of all, let's try delta equals Let's try delta is on the order of square root of n. Okay, so basically you're saying what's the probability with n flips I get more than n over 2 plus square root of n number of heads. Okay, Right, now if delta equals square root of n, then here you have this delta squared term. So then this is going to be order of n. Okay, yeah. So if you plug in square root of n onto the into this formula over here, you're going to get that the probability is basically e to the negative order 1. Okay, so order 1 is some sort of constant. So this whole thing is going to come out to some constant. Okay. In other words, the probability that you get more than order square root n heads more than your expectation, right? There's only a constant probability of getting square root n more heads than your expectation. Okay, that's what this says. Okay, does that make sense? Okay. All right. So so next, let's try a different value of delta of lambda. Okay. So suppose you make lambda even larger. So it's not square root of n anymore. Now we're going to make it square root of n times square root of n log n. Okay. So now you expect the probability that you get this deviation to be even smaller. Right. The larger lambda is, the smaller the probability. Okay. All right. So then let's just plug in this lambda into this exponent over here. Okay. And when you do that, you're going to get basically negative order log n. Okay, and so this says that the probability you deviate by more than lambda for this value of lambda is going to be e to the negative order log n. Okay, now if you simplify this expression, what you're going to get is 1 divided by n to some constant. Okay, to some positive constant. Okay, so this means that it's basically so it's basically polynomially unlikely that you're going to get such a large deviation, a deviation by more than lambda. Okay, perhaps there should be omega instead of big O. Yeah, sure. Okay, you could say omega also. Here, we should maybe let's make this theta. Okay, yeah, you're right. Let's make everything theta over here, so that we can say that, because if it's big O, lambda could actually be quite small. Okay, but actually, I'll just mention that in practice, people tend to use big O to just mean the same thing as big theta. Okay, like if you're talking in a rigorous sense, these things are not equal to each other. But oftentimes, people in practice, they just write big O to mean big theta. Okay. Yeah, but you're right that, if we want to be careful about this, we should actually write big theta instead of big O. Okay, yeah. So what this bound says is that if it's actually, there's a polynomially small probability, okay, 1 divided by n to some constant probability that you deviate by more than square root of n log n. And so, in fact, this type of expression, the 1 divided by n to the c, okay, this comes up quite often when you analyze randomized algorithms, okay? And in fact, it comes up so often that people give this a name, okay? So if an event happens with probability at least 1 minus n to the negative c, okay, for some c larger than 1, okay, then you say that this event happens with high probability. Okay, basically what's happening here is, suppose let's say c just equals 1 over here. Okay, then you're saying that this event, happens with at least 1 minus 1 over n probability. Okay, and so this means that as n gets larger, the probability of this event happening gets larger and larger. Right, so that's why we say that this event occurs with high probability. Yeah, so in our case, what we're saying is that the probability you get, so here the probability you get more than lambda deviation is smaller than 1 divided by n to the c. Okay, so that means that the probability you get at most n over 2 plus order of root n log n heads. Okay, that occurs with probability at least 1 minus n to the negative c. Okay, so that occurs with high probability. Okay, yeah, so that's what, the first application of Chernoff bounds. Okay, so sort of another sort of more pictorial way to see this is that if you look at the number of heads you get and you plot the probability distribution, okay, then okay, so all right, can you guys still hear me? So I plugged in a microphone. Can you still hear me? Okay, all right, good. Okay, so another more pictorial way to look at this is that if you plot the probability distribution of getting different numbers of heads, okay, then because you expect to get n over 2 heads, then n over 2 actually has the highest probability, okay. And then if you look at the probability of getting some number of heads which is centered around your expectation, okay, so let's look at a region which has width root of n log n and which is centered around our expectation, okay, then the probability your number of heads falls within this region is going to be at least 1 minus 1 over n to the c. Okay. In other words, if you look at this this green region, which is outside of the central region, okay, then the total probability mass in that green region is going to be at most 1 over n. Okay, so the probability that you get basically what you expect is going to be at least 1 minus 1 over n. Okay, any questions about this? Okay, so let's do another example of this, of using Chernoff bounds to analyze algorithms. Okay, so now we're going to look at a problem called load balancing. Okay, so the situation is that you have, let's say, n computers. Okay, so all of these computers are working in parallel, and now you have a bunch of jobs or tasks for these computers to execute, and these tasks are just arriving one by one in some sort of random fashion. Okay. And what you want to do is each time you get a task, you want to give it to one of these computers to execute that task. Okay. And furthermore, since you want to finish all of the tasks as quickly as possible, you want to load balance between all of the computers, meaning that you want all the computers to have about the same number of tasks. Okay, that way, everybody's working, all the computers are working all the time, and so that allows all the computers to finish as quickly as possible. Okay, we're going to make the simplifying assumption that each task has the same size. Okay, so yeah, so so as long as all the computers get the same number of tasks, then their load on each computer is balanced. Okay, so the question is, how do we achieve this load balancing? Okay, so this is actually a very practical problem, right? So in a parallel computing setting, this is exactly the type of problem that you need to deal with. All right, so there are many ways actually to do load balancing. Okay, so one simple way is this method called round robin. Okay, which means that each time a job comes in, you just give it to the next computer. Okay, so the first job you give it to computer 1, next job you give it to computer 2, and then computer 3, and so on. And let's say you have 10 computers. Okay, then for the 11th job, right, you're going to give that back to computer 1. Okay, the 12th job goes to computer 2, and so on. Okay, so we just cycle through all of these computers. Okay, so this is a very simple method, right? And it actually achieves very good load balancing. Okay, basically it's a perfect load balancing, okay, or as perfect as you can get. However, one drawback to this method is that you need to have like a centralized controller which keeps track, or scheduler process, which is keeping track of which job or which computer got the last job. Right. So somebody needs to know, like, the last job went to computer 3, so therefore the next job goes to computer 4. Okay, you need to have some sort of central scheduler process like that. Okay. And if you have lots and lots of computers, then this scheduler process can become, there can be a bottleneck at the scheduler process. So therefore, we want some sort of more autonomous way for the computers to balance their load. So we're going to look at something called randomized load balancing. And yeah, so this is very simple. It's all you do is whenever you get a new job, right, you just give it to a random computer. Okay, that's all. Okay, you don't try to keep track of which computer got the last job. Just anytime you get a job, you give it to a random computer. Now, if you think about this, this is a reasonable thing to do. Right? Because if you keep giving jobs to random computers, then you expect that all the computers are going to end up with approximately the same number of jobs. Okay, so now let's analyze how good this load balancing algorithm actually is. Okay, and we're going to use Chernoff bounds to do this. Okay, so suppose that you have m jobs in total. Okay, and let's say you have n computers. Right. So then in expectation, every computer is going to get m divided by n jobs. Okay, but of course, in practice, you could actually deviate from this expectation. Okay? But we're going to use Chernoff bounds to show that it's unlikely you deviate substantially from this expectation. Okay, oops. All right. So to do this, let's define an indicator let's define a random variable xi, which is equal to the number of jobs that computer I gets. Okay. And also let's let capital X here be the maximum over all the xi's. Okay. So this is like the largest number of jobs that any computer gets. Okay. And we don't want this x to be too large. Right? We want this x to be approximately the expectation, to be approximately m divided by n. Okay. All right, so we're going to bound the probability that xi and x are very large compared to the expectation. Okay, and if we can show that with very high probability they are close to the expectation, then this means that the load is roughly balanced with high probability. Okay, so to bound xi and x, we're going to define an indicator variable yij. Okay, so this is going to be this yij is going to be 1 if the jth job is assigned to the ith computer. Okay, and 0 otherwise. Okay, so yij is simply an indicator for whether you assign the jth job to the ith computer. Okay. And now, first of all, the probability that yij equals 1, okay, this is equal to 1 divided by n. Because for each job, you just assign that job randomly, okay? And so for so since you have n computers, right, then the probability that the ith computer gets the jth job is just 1 over n, right? Because you take the jth job and you give it to a random computer among your n computers, okay? So the probability that the ith computer gets it is just 1 over n. Okay, also xi here, right? Xi is the total number of jobs that the ith computer gets. Okay, and this is just equal to the sum over j of yij, right? So we're summing here over all the jobs, right? J represents jobs, okay? So we're summing over all the jobs, and for each one, we're looking at whether the ith computer got the jth job. Right, so if you sum that up, that's just equal to how many jobs computer I got. Okay, and now because we're assigning each job completely randomly, right, then all of these yij's, they are independent random variables. Okay, and because xi is the sum of all of these yij's, then you can apply the Chernoff bound to analyze xi. Okay, so let's do that. Okay, so so again, we're going to consider different cases. We're going to vary the number of jobs that you have. Okay, so sometimes you have like a very small number of jobs, and other times you might have lots of jobs. Okay, so the first case we're going to consider is that the number of jobs is equal to the number of computers. Okay, so here we only have a few jobs. All right, now in this case, the expected number of jobs that each computer gets is just going to be 1, right? Because it's m divided by n, right? Or actually, let's do this analysis, okay? So mu here is the expected number of jobs that xi gets, okay? And this is equal to the sum of all of these yij values, right? And each of these yij values is going to be, the expectation of each of these yij's is 1 over n, right? So in total, we have that the expected number of jobs that each computer gets is m divided by n, which is equal to 1 in the case that m equals n. Okay? All right, so now let's look at the probability that we deviate from this expectation of 1. Okay? So of course, you get to define how large of a deviation you want to consider. Okay, so in this case, let's suppose we want to look at a deviation by a factor of log n divided by log n. Okay, so I just chose this factor because Yeah, because this is going to make things work out nicer. Okay. Yeah. So let's look at a probability that you deviate by this amount, by this multiplicative amount. Okay. And we're going to show that this probability is very small. Okay. Okay. Yeah. So in our case, we're looking at a deviation by a factor of log n over log n, and so this is going to be our delta here. Okay. So now you can just plug in this expression into the Chernoff bound. Okay. So we're going to use a theorem 1 and part 2 of the Chernoff bound. Okay. And that basically says that your probability is no more than well, if you plug things in, you're going to see that this is going to become your probability. Okay, it's going to be no more than e to the negative delta log delta divided by 3, where delta is this log n divided by log n. Okay. All right. Now, if you simplify this, right? So we're going to yeah. So if you compute this, where delta is this thing up here, right? Then all of this is going to come out to basically e to the sorry, this should be a negative here. Okay. E to the negative order log n. Okay. All right. And so by choosing the right constants, we can make sure that this probability is no more than 1 divided by n squared. Okay. In other words, you have at most a 1 divided by n squared probability of deviating by a factor of more than log n divided by log n. Okay. Yeah. So each computer has a less than 1 over n squared probability of having a large deviation. Okay, but we're not just looking at each individual computer. We want to look at the probability that any computer, okay, has such a large deviation. So in total, we have n computers, right? So the probability that any computer has such a large deviation is at most going to be the n times the probability that any computer has such a large deviation. Okay, so this is called the union bound. Okay, so the union bound is basically saying that the probability that two events A or B happen, right, is going to be at most, the probability of A, right, plus the probability of B. Okay, now in our case, we have n different events that we're considering, right? We're looking at what's the probability computer 1 gets a large deviation, or computer 2 gets a large deviation, or computer 3 gets a large deviation, and so on. Okay, so in total, we have n different events that we're looking at, and the probability that any of these events happens is going to be no more than the sum of all of the individual probabilities. And each individual probability is 1 over n squared. And you have n of these events, so the probability that any of them happen is at most 1 divided by n. Okay, and so that means that this x here, right, this is the largest xi. Okay, and so the probability that even the largest xi is larger than this log n over log n. Okay, this is at most a 1 over n probability. Okay, any questions about this? All right, so so this part is saying that we're not going to get a very large factor deviation, right? You're not going to deviate by more than a factor of log n over log n. Okay? But this is still a pretty substantial deviation, right? Because this means that some computers have log n factor more than other computers in terms of load, right? And the reason this is happening is because here we only have a few jobs that we're looking at. Okay, so this is kind of like if you only flip a coin a few times, then it's possible that there's actually a pretty high probability that you get lots and lots of heads, right? If you only flip the coin a few times. But you expect that if you flip the coin more and more times, then it's going to be much less likely that you get lots of heads. Okay, and so what we're going to see now is that suppose now you have more jobs. Okay, so instead of just having n jobs, you have something like n log n jobs now. Okay, times this factor 16, which is used to make the math work out. Okay, so but basically here you have more jobs now, right? And the more jobs you have, the more balanced you expect these computers to be. Okay, and so now we're going to look at if you have this number of jobs, we're going to look at the probability that you have large deviations. Right, now, first of all, when you have 16 n log n jobs, right, then since you have n computers, you expect each computer to get 16 times log n jobs. Okay. And now let's look at the probability that any computer, that some computer xi, let's look at the probability he gets more than 2 times his expectation. Okay. All right. So in this case, we're going to use theorem 2. Okay, so you guys can flip to theorem 2, which is just some other version of the Chernoff bound. Okay, and if you plug all the numbers into theorem 2, right? So I'll just show you what theorem 2 says. Let's go back to theorem 2. Yeah, so theorem 2 has this sort of complicated expression over here. Okay, but all of these are just this entire thing here is just a constant once you fix delta, right? Yeah. Okay, so anyways, if you plug in, or sorry, it's not a constant, but it's like a fixed formula once you fix delta. Okay. All right. So in our case, we are going to be looking at delta equals 2 in our case. Okay. So then if you plug in all that thing into that formula, and then you simplify, you're going to end up that you're going to end up getting that the probability you get more than 2 times your expectation is at most 1 over n squared. Okay, and so now, once again, we can use the union bound to bound the probability that there's any computer, that even the largest computer gets more than 2 times the expectation. Okay, and that's just bounded by n times this individual probability over here. Okay, which is going to be 1 over n. Okay, so this means that you have a very low probability. You have a 1 over n probability that any computer deviates by more than a factor of 2 from its expected load, right? So that means that all the computers are pretty balanced on average. Okay, at most they're off by a factor of 2 from each other. Okay, all right. Now one final thing we're going to look at is so this says that no computer has more than 2 times the average load. Okay, but you also want to make sure that none of the computers have much less than the average load. Okay, so let's look at what is the probability that any computer has less than half of the expected load. Okay, and to do this, we're going to use part 3 of the Chernoff bound, theorem 1. Okay, so you guys can go look up what part 3 says, but basically, if you plug in all the constants, okay, then you're going to find that the probability any computer gets less than half of the expected load is going to be 1 over n squared. Okay, it's once again 1 over n squared. Okay, so in fact, this is why I chose this factor 16 over here. Right? The reason I chose this factor 16 is because there are all these sort of constant factors in the Chernoff bounds, and I want to make sure that they all cancel out. Okay, so if you use 16, you can make sure all the bounds work out the right way. And you get that both the probability you get more than twice the expected load or less than half the expected load, okay, both of those are going to be at most 1 over n squared. Okay, and so again, if you use a union bound, the probability that even the smallest computer, right, the computer with the fewest jobs, the probability that one has less than half the expected load is going to be at most n times this probability, which is going to be 1 over n. Okay, so therefore, in conclusion, we have that with high probability, right, with at least 1 minus 1 over n probability, every computer has between half and twice the average load. Okay? Are there any questions about this? Okay. And yeah, and in fact, if you increase the number of jobs even more, okay, then the larger m is, basically the smaller you can make this factor over here and still get the same high probability bounds. Okay, yeah, because all you care about for the Chernoff bound is the final thing that appears in the exponent. Okay, the exponent is a product of the deviation over here, right, and the expectation. Okay, so the larger the expectation, the smaller you can make that deviation and still get the same probability bounds. Okay, so it's a question here, page 10. We don't know. Page 10. Okay, so I think which one is page 10? Sorry, a second. Page. Oh no, sorry, this is the wrong thing. Sorry. Load balancing, page 10. Oh, okay. Page 10, we don't know how lambda is positive or negative. Sorry. Lambda is going to be positive. Okay. Yeah. Sorry. I forgot to say that. Yeah. Lambda is a positive number. Yeah. So you're looking at what's the chance I get more than the expected number of heads. Okay. Any other questions? Okay, so then we're going to look at one final application of Chernoff bounds. Okay, and this is going to be for a problem called set balancing. Okay, so let me introduce this problem first. So suppose you have a bunch of sets. Okay, you have m sets, where each set is a subset of the numbers 1 up to n. Okay. And so now you can represent each set as an m-bit vector. Okay, so for example, if you have if n is equal to 4 here, and if your subset is 1, 3, 4, okay, then you can represent that as this bit vector, right? So you set the first component to be 1, you set the second component to be 0 because you don't have a 2, right? And then you've got a 3 and you've got a 4. Okay, so that's how you represent that set. Okay, right. And now, suppose you have m sets in total. And what you want to do is to divide these m sets into 2 groups, okay, such that these 2 groups are roughly balanced with each other. And what I mean by balanced is that if you add up the total number of occurrences of each element in each group, then they're roughly balanced. Okay, so let me give you an example of this. Okay, so suppose you have here you have 4 sets. Okay, so you have S1 up to S4. Okay, so the first set is going to be 1, 3, 4, right? The second set is 1, 2, 3, right? The third set is 3, 4, and so on. Okay, and now you want to take these 4 sets and you want to break them into 2 groups which are roughly balanced. So suppose you break them into groups S1 and S4 you put into the first group, and S2, S3 you put into the other group. Okay, then S1, if you look at S1 and S4, then they have a total of 1 copy of 1, right? They have a total of 1 copy of 2. They have 2 copies of 3, and they have 1 copy of 4. Right? If you take S1 and S4, right, then S1 has a 1, but S4 doesn't have a 1. So in total, you've got a single 1 here. Okay, and you've also got a single 2 from S4, and you have 2 3s. Okay, because S1 and S4 both have 3s, and you have a single 4. Okay, and then if you look at S2 and S3, well, altogether, they also have a single 1, a single 2, 2 3s, and 1 4. Okay, so this means that S1, S4, and S2, S3 are balanced groups. Okay, and our goal is that if I give you m sets to start with, okay, can you divide these sets into 2 groups which are balanced with each other? Okay, that's what we're trying to achieve. Okay, so it might be possible that for certain sets, it might be impossible to exactly balance these sets, right? I mean, you could imagine that. Let's see. Do I have an example of this? Well, I guess I have an example later. Okay, but you can imagine that if I give you certain sets, then no matter how you divide these sets, you cannot exactly balance the 2 groups. Okay, so in that case, what we're going to do is look for a grouping that's as good as possible, that's as balanced as possible. Okay, so what do we mean by as balanced as possible? Well, suppose let's let G and G prime be the 2 groups. Okay, so G is a bunch of these sets, right? And then G prime is the remainder, is all the remaining sets. Okay, right. Then, in order to make these 2 groups as balanced as possible, what you want to do is to minimize the maximum imbalance. Okay, and so what I mean by that is we're going to take the first group and you add up all of these sets. Okay, just like, here we added up all of these sets. Okay, and then you take the other group and you add up all their sets. Okay, and now if you subtract, so now you're going to get basically two vectors. Okay, the vectors have n bits in them, right? Or not n bits, but n values in them. Okay, so this is going to be a size n vector. This is going to be a size n vector. And now if you subtract these two vectors, okay, then that's going to tell you the imbalance for each of these elements, for each of the n elements. Okay, and now let's look for the element which is the most imbalanced. Okay, and so that is going to be that's going to be the quantity that we want to minimize. Okay, so let's do an example here. Okay, so suppose you have again you have 4 sets. Okay, and now it turns out that for these 4 sets, it's not possible to exactly balance them. Okay, however, if you use a grouping S1, S3 in one group, right, and S2, S4 in another group, right, then if you add these things together, you get this is your first vector for the first group, that's for the second group, and now if you subtract them, you're going to get this thing. Okay, this vector. So what this says is that these two groups have the same number of 1s and the same number of 2s. Okay. However, group 1 has a 1 more 3 than group 2, right? And they also have the same number of 4s. Okay. So therefore, the imbalance is just whichever component in this final vector is largest. That is your imbalance. Okay. And we're trying to minimize that quantity. Okay, does that make sense, what the problem is? Okay, yeah, so you need to look for some way to divide your set into 2 groups such that when you compute this quantity over here, right, this is going to be as small as possible. Okay, and this quantity represents, which element out of your n elements, okay, which one is the most imbalanced between your 2 groups. Okay, so so if you do this, okay, so now we need to find an algorithm, and one thing you can do is you can just try all possible groupings of these 2 sets, of these m sets. Okay, but if you try all possible groupings, then since you have m sets, right, there are 2 to the m possible groupings. Okay, so this is this would be an exponential time algorithm. Okay, right. So instead, we're going to look at a very simple randomized algorithm. Okay. And sort of surprisingly, this very simple randomized algorithm is going to ensure that your maximum imbalance is actually not too large. Okay, it's going to ensure that at most your imbalance is on the order of 4 times your number of sets times the number times log of the number of elements. Okay, so in other words, it's going to make sure that any element does not occur more than this number of times more in one group compared to the other group. Okay, and this is going to happen with high probability because it's a randomized algorithm. Okay, yeah. So if you compare this with the maximum imbalance of any element, right? The maximum possible imbalance is m because you could have an element which is just completely in one group of in one of the groups and does not occur at all in the other group. Okay, in that case, you could have an imbalance of m. Okay. But what we're saying is that for this randomized algorithm, your imbalance is on the order of square root of m. Okay, so it's much smaller than the maximum possible imbalance. Okay, and this algorithm is very, very simple. Okay, so that's why it's surprising that it works so well. So the algorithm is simply that for each set, right, you just put it into a random group. Okay, you have 2 groups. Okay, so you just go through all your sets. And for each one, you either put it in the first group or the second group randomly. Okay, that's all you do. And yet, this works quite well. Okay, so let's analyze this algorithm. Okay, so let's see why it works so well. Okay, so what we're going to do is look at some particular item I. Okay, and now this item might belong to k of your m sets in total. Right, so for example, if you look at this example over here, okay, then if you look at the third element, right, it belongs to 4 sets, okay, because all of the sets have the third element, okay. if you look at, what do we do? If we look at the second element, okay, then the second element actually belongs to only 2 of these sets. Okay, right. So then we're going to look at some element I, and suppose that I belongs to k different sets. Okay, and now for the jth set, which I belongs to, okay, so in total I belongs to k sets, and if you look at the jth such set, okay, then let's define x of j to be 1 if so we're looking at the set S, and then x of j is going to be 1 if the set is put into the first group, and x of j is going to be -1 if it's put into the other group. Okay, remember that for each set, you randomly put it into either the first group or the second group. Okay, so we're going to set x of j to be 1 if S is put in the first group, and -1 otherwise. Okay, so in that case, the imbalance that you have for the ith item, okay, is simply the sum of all of these xj's, right? Because for example, if you look at all of the k sets that this ith item belongs to, right? And if in half the cases they go in the first group, so in half the cases you get a +1, and the other half of the cases you get a -1, right? Then there's no imbalance at all for that item. Okay, and so if you just add up all of the xj's, you get 0, right? Which tells you that there's no imbalance. Okay? Yeah. So in any case, if you add up all of these xj values, then that is exactly equal to the imbalance for the ith item. Okay, so bi here is equal to the imbalance for the ith item. Okay, so now since we assigned all of these sets randomly to either the first or second group, okay, then all of these values x1 up to xk are independent of each other, right? And their values are either 1 or -1. Okay, so in that case, now we can apply theorem 3, version 3 of the Chernoff bound. Okay, and that allows us to bound the maximum value for any of these bi values. Right, so the bi is the imbalance for the ith element, but we want to make sure that all the elements are not imbalanced. So therefore, we want to bound the maximum of all the bi's. Okay, so yeah, so we're going to use version 3 of the Chernoff bound, and we're going to consider 2 cases. Okay, so the first case is where k here is small. Okay, and the other case is where k is large. Okay, yeah, so when k is small, right, then that means that this ith item here only belongs to a few sets, right? So by small, we're going to set this to be just this quantity over here, okay, square root of 4m times log n. So if k is less than this quantity, then you know your maximum imbalance is at most this k here, right? Because if the ith item only belongs to k sets, then the maximum imbalance for I can be at most k. So if k here is actually a small value over here, then we're guaranteed that your imbalance is going to be no more than k. Okay, it's going to be small. Okay. On the other hand, if k is large, okay, if k is large, then we can use the Chernoff bound. Okay. So if k is larger than that value, then if you apply theorem 3 of the Chernoff bound, right, you're going to see that if you after you go through all the math, you're going to see that the probability that you get a large deviation, right, is going to be at most 1 over n squared. Okay, and this bi exactly represents the imbalance for the ith element. So this is saying that the ith element is very imbalanced with only a 1 over n squared probability. Okay, and so once again, after this, we can apply the Chernoff. We can apply the union bound, which says that if you look at any of the n items, okay, the probability that any of these n items has a large imbalance is going to be at most n times this, which is going to be 1 over n. And so that means that with probability at least 1 minus 1 over n, we have that all of the items do not, the imbalance for all of these items is going to be at most root 4m log n. Okay, so this shows that this randomized algorithm, this very simple randomized algorithm, actually guarantees that you have low imbalance. Okay, or actually, with high probability, right? It shows that with high probability, every item has a low imbalance. Okay, because if the item belongs to only a few sets, then automatically you have low imbalance, and if the item belongs to many sets, right, then by the Chernoff bound, you have a very low probability that this item becomes imbalanced. Okay, any questions about this? Okay, so that's all I have to say for Chernoff bounds, and so now we're going to move on to the next topic. Okay, so the so the next topic is going to be so we're still going to talk about randomized algorithms, but now we're going to look at randomized algorithms and how they're used in distributed computing. Okay, all right. Now, first of all, what do I mean by distributed computing? So we're basically going to look at a distributed system. Okay, so a distributed system is you have a so imagine that you have a bunch of nodes, and all of these nodes are working independently from each other. Okay, and then the nodes sometimes might be able to communicate with each other, but when they communicate, you have to pay a cost. Okay, so therefore you want to minimize your amount of communication. Okay. And even though the nodes are working independently, sometimes they need to get together and do some sort of cooperative task. So an example of this would be like a blockchain. Okay, in a blockchain, you have a bunch of these miner nodes, right? So all of these miners are working independently to mine these blocks. Okay, but once in a while, they need to cooperate in order to add the next block into the blockchain. Okay, so when they need to cooperate, they need to run some sort of algorithm with each other, some sort of consensus algorithm. Okay, and in that case, they need to do some sort of communication. Okay, but because all these nodes are distributed, then the communication comes with a cost, and so therefore we want to minimize the amount of communication that nodes do. Okay. Another example of a distributed system would be if you imagine a bunch of sensor nodes. Okay, so suppose these sensor nodes are sensing so they're distributed over, let's say, like a field. Okay, and all of these sensor nodes are sensing the temperature at different parts of this field. Okay, and then so they're all working independently, but once in a while you want to get the average temperature over this entire field. Okay, so in that case you want to aggregate all of the values at these different sensors, right? And when you do that, you need to have some communication between these sensors. But you want to design your communication protocol to minimize the amount of communication, because these sensors are working probably using batteries, and so each time they communicate, they have to use up a large part of their battery. Okay, so therefore you want to minimize the amount of communication that they do. Okay, so these are examples of distributed systems. Yeah, okay, so the internet is also a distributed system, right? Computer clusters and so on. Okay. And the point is that sometimes these nodes need to solve some sort of cooperative task. And when that happens, we want to minimize the amount of communication that we use. Okay. And it turns out that one good way to minimize the communication is to use a randomized algorithm. Okay. So when you make, if you make the nodes behave in a random fashion, right? If you use a right randomized algorithm, then this can sometimes dramatically reduce your amount of communication. So this is one application of randomization in distributed computing. Okay. Another reason why randomization is useful in distributed computing is because it helps you do symmetry breaking. Okay. So what I mean by symmetry breaking is that, since you have a bunch of autonomous nodes, right, then each node basically thinks that it is equivalent to all of the other nodes, right? There's no real difference between any of the nodes. Okay, so all the nodes are symmetric to each other. However, for certain problems, you don't want all the nodes to be symmetric to each other. For certain problems, you might want to pick out a special node. So for example, you might want to pick out a leader node, and only that leader node gets to do something. And all of the other nodes need to listen to that leader node, need to follow that leader node. Okay, so in that case, you want to break the symmetry between all the nodes so that you get a single leader node and all the other nodes are not leaders. Okay, and this is oftentimes hard to do in a distributed system because all the nodes think that they are equivalent to each other. Okay, because when you start out, all the nodes think they're equivalent to each other. Okay. So randomization actually gives you a very easy way to break the symmetry. Okay, because for example, you can have the nodes pick random numbers. Okay, so if a node happens to pick let's say a large random number, then it can become the leader. Okay, and if the nodes pick small random numbers, then they are not the leader. Okay, so just by picking a random number, you can automatically break the symmetry between the nodes. So that's another way that that randomization is used in distributed computing. Okay. All right. So today we're going to look at two problems where you use randomization. Okay. So the first one is called contention resolution, and the other one is maximal independence set. Okay. So let's first do contention resolution. So the problem here is that suppose you have n distributed nodes, okay, and they all want to communicate with each other. So these can be like cell phones or sensors or something like that. Okay, so they all want to communicate with each other. Okay, and let's assume that these guys are using wireless communication. Okay, so the problem with wireless communication is that in many circumstances, you can only have one node which sends messages at a time. You cannot have many nodes sending at the same time. Okay, and the reason is because so for example, if you consider a bunch of nodes like this, okay, so each node wants to communicate with all the other nodes. So it's going to send a wireless message, and this wireless message is going to have some sort of coverage. Okay, so for example, if this node sends a message, right, then the message can reach this area, this circular area. Okay, and now suppose you have some other node which sends messages at the same time. Okay, so then its message can also reach some sort of area, okay, like the second circle. And so what happens is now, if you have, let's say, a third node over here. Sorry, what happened to my circle? Okay, if you have this third node marked with an X, right? Then this third node is going to get messages from these two other nodes at the same time. Okay, and these two messages can cause interference with each other. Right? So, for example, if they're transmitted at the same frequency, then these two messages from the top nodes are going to interfere at the third node, and then the third node can't hear anything. Okay, so to avoid this interference, what you want is you'd only want sorry, can't I erase over here? Okay, so all right, fine. Okay, yeah. All right. So, anyways, what you want in order, okay, sorry. What you want in order to avoid interference is that you only want one node to transmit at a time. Okay, and that's gonna yeah, so that way you won't have any interference in your communication. Okay, and so this is why the problem is called contention resolution, because all of the nodes are trying to send messages. Okay, we assume that each node has a message that it wants to send to all of the other nodes. But if two nodes send at the same time, then both their transmissions are going to fail. Okay, so we basically want a way for these nodes to sort of coordinate with each other, so that every node can send a message at some time point, and at a time point where it is the only node that is sending. Okay, and there are no other nodes which are also sending at the same time. Okay, so to do this, you can try to work out some sort of schedule between the nodes. Okay, so for example, you can say that node 1 is going to send first, and then node 2 is going to send, and then node 3 is going to send, and so on. Okay, but the problem is that in order to work out the schedule, so initially you don't know how many nodes there are, right? Initially the nodes do not know about each other. So in order for them to work out a schedule, then the nodes need to, presumably they need to do some sort of communication with each other in order to work out a schedule. Okay, but the problem is that the nodes cannot communicate, right? Because the whole problem that we're trying to solve is in order for all the nodes to communicate with each other, right? Each node has a message and it wants to send that message to the other nodes. So it wants to do some communication with the other nodes, right? So to solve this communication problem, you can't assume that you already are able to communicate. Okay, yeah. So in other words, it's hard for nodes to work out a schedule among themselves. Okay, so instead, we're going to look at a randomized algorithm, which is going to allow all the nodes to send their messages. Okay, now so we're going to work in a special setting which is called a synchronous setting. Okay, And this means that the nodes are going to work in rounds. Okay, so imagine that all of the nodes have clocks, right? And using those clocks, they can divide time into different rounds. Okay, so for example, it's 10 o'clock now, and then the next round occurs at 10:01, and then 10:02, 10:03, and so on. Okay, and so we assume that all of the clocks, all of the nodes have synchronized clocks, so they all know when different rounds start. Okay, so the nodes are going to work in rounds, and the algorithm is that each node will try to send once per round, or could try to send once per round. Okay. And the round is successful if during that round, there's only a single node which tries to send in that round. Okay, so in a round, you could either have like no node tries to send, okay, in which case you don't have any communication, okay, or you could have lots of nodes trying to send, and in that case, they're going to interfere with each other, and again, you don't have any successful communication. And the only case where you have a successful communication is if there's only a single node which tries to send in that round. Okay, so then how does a node decide whether to send in a round? Okay, well, the algorithm is that each node is going to try to send with a probability of 1 divided by n in each round, where n is the number of nodes. Okay, so we assume that the only thing the nodes know about the system is the total number of nodes, is this value n here. And then each node is going to try to send with a probability of 1 over n in every single round. Okay. And again, the round only succeeds if there's a single node which tries to send in that round. Okay, so the question is, so we want to make sure that all the nodes get to send their own messages. Okay, so the question is, how many rounds does it take before all of the nodes can send their messages? Okay, so we want to analyze this. Okay, so to do this, we're going to define an indicator here, SIT. Okay, so this is going to be the event that node I successfully sends in the tth round. Okay, and in order for this SIT to occur, this can only occur if, first of all, I itself does try to send in the tth round. Okay, and furthermore, all of the other nodes do not try to send in the tth round. This is the only way for I to successfully send its message in the tth round. Okay, so then what is the probability that SIT occurs? Okay, so the probability is that, well, first of all, I itself has to try to send a message. Okay, and this occurs with probability 1 divided by n. Right, that's our algorithm. Okay, every node in each round sends with 1 over n probability. Okay, and then furthermore, all of the other nodes have to not try to send. Okay, so the probability that one node does not try to send is just 1 minus 1 over n. Okay, and you have m minus 1 other nodes, so therefore the probability that all of them do not try to send is just this expression over here. Okay. All right. So therefore, the probability that that I succeeds in the tth round is going to be given by this this formula over here. Okay. All right. So we want to simplify this formula. So we're going to use this math fact over here, which is we're basically going to estimate what this value is. Okay. So we have two bounds. So we know that this value here is going to be at least 1 divided by e. Okay. And at most 1/2. For n larger than 2, for n at least 2. Okay. Yeah, and then right, and then this other bound here is so if this exponent here is n instead of m minus 1, right, then you have that this is going to be at least 1/4 and at most 1 over e. Okay, so those are just two facts. Okay, so using those facts, then you can plug them into this formula over here, and you're going to get that the probability SIT occurs is going to be at least 1 divided by e times n. Okay, so that means that in each round, right, for one particular node I, it's got a 1 divided by e times n probability of sending in that round. And so that also means that the probability that it fails to send in a round is going to be 1 minus this probability. So it's going to fail with at most 1 minus 1 over en probability. Okay, so now using this, we can prove that that if you run for 2e times n log n rounds, okay, then all of the nodes will succeed in sending with high probability. Okay, so the optimal thing would be that if every node sends in each round, okay, then in total it would take you n rounds, right? Because each round you can only have one node sending. So the fastest possible speed, the minimum number of rounds to send all the messages is n. And then here we're saying that with this randomized algorithm, you can basically send all the messages in n log n rounds. Okay, so it takes you a factor of log n more rounds to send all the messages with high probability. Okay, so to do this analysis, let's let fi be the event that node I fails to send after this number of rounds. Okay, so we want to make sure that fi doesn't happen, right? And then f here is going to denote the event that any node fails to send after these number of rounds. Okay, so our goal is to show that f does not happen. Okay, so to do this, let's first analyze the probability of fi. Okay, so we said that in each round, the ith node fails to send with at most a 1 minus 1 over en probability. Okay, and so that means that if you run for 2e n log n rounds, right, then the probability that the ith node fails to send after all of these rounds. Okay, so all of these rounds are independent from each other. So therefore, the probability that the ith node fails to send after all of these rounds is going to be this expression over here. Okay, right. So now you can simplify this expression a bit. You can basically you can take this en term and you can sort of pull it out. And so what you get is here you basically get something like 1 minus 1 over en to the en. Oops. Okay, to the en. Okay. And this whole thing to the 2 times log n power over here. Okay, so these two things are equal. And this thing, what happened? Right, and this thing over here, okay, so the part within the parentheses, you can basically estimate that by 1 over e. Okay, right, so therefore this whole thing is going to simplify to basically 1 over n squared. So that means that oh, sorry. This fi is not talking about the ith node. It's oh yeah. Right. Okay. So it's saying that the ith node after it runs for 2n log n rounds, okay, the probability that it still fails to send in any of these rounds is going to be at most 1 over n squared. Okay. And so the final thing is that we want to look at the probability that any node fails to send after this number of rounds. And so once again, we're going to use the union bound, right? So you guys see the pattern now, right? So usually in these analyses, we're going to look at the probability that some individual node or something fails, right? And then we're going to finish up by using the union bound over all of the nodes. Okay. So if you use a union bound, you're going to see that the probability any node fails after this number of rounds is going to be at most 1 over n. And so that means that all of the nodes are going to succeed with probability at least 1 minus 1 over n after that number of rounds. Okay, so once again, what we did was we used a simple randomized algorithm, and then the performance that you get, right, the number of rounds you take, is basically a log n factor larger than the optimal performance, which is n. Okay, any questions about this one? Okay, all right, so then next we're going to talk about another problem, which is maximal independent set. Okay. All right, so first of all, let me define what an independent set is. So if you're given a graph, then an independent set is a subset of the vertices of this graph. And the requirement is that when you all the nodes in the independent set are not connected to each other. Okay, so so let's just do an example over here, right? So so here I have like 6 different graphs. Okay, And what I did was to mark out the independent sets in red. Okay, so for example, in the first graph, right, you see that if you these two red nodes are not connected to each other. Right? And in the second graph, right, you see that we have 4 red nodes, and all of them are not connected to each other. Okay. Now, something which would not be an independent set is if I choose this node also. Okay, then these 3 nodes would not form an independent set because they would touch each other. Okay, yeah, because 2 of the nodes are connected. Okay, but I could add this node over here. Oops, I could add this node, right? And in that case, these 3 nodes still do not are not connected to each other. Okay, so the problem we want to solve is a maximal independent set. Okay, and this is basically an independent set which is as large as possible in the current circumstance. Okay, so what I mean by that is, suppose I give you a set of nodes, okay, and which are independent. Okay, now if it's the case that I cannot add any additional nodes and still have an independent set, okay, then this is a maximal independent set. Okay, so as an example, so if you look at this second graph over here, okay, then here I cannot add any additional nodes and still have an independent set, right? Because, for example, if I add this node, okay, then these 2 things are connected, so that's not independent anymore. Okay, so you can check that for all of these 4 yellow nodes that I haven't added yet. Okay, I cannot add any of them and still have an independent set. And so therefore, the second graph here is a maximal independent set. Okay. On the other hand, if you look at this graph over here, right, if you look at the first graph over here, right, then you see that it's possible to add some additional nodes, right? So for example, we can add these 2 other nodes, and we still would have we still would have an independent set. Okay. So that means that the initial graph is not maximal because you can make it larger. Okay. Yeah, so so the problem we're trying to solve is to find a maximal independent set. Okay, and again, this is an independent set which cannot be made any larger. Okay, now before we actually look at how to solve this problem, I just want to contrast this maximal independent set with a very similar problem, which is maximum independent set. Okay, so I'm going to write maximal as MIS and maximum as MAX-IS. Okay. Now the difference between maximum and maximal is that for maximal, all we're saying is that you have an independent set and you cannot make it larger. Okay. Otherwise, yeah, you cannot make it larger. For maximum independent set, what we want to do is to look at all possible independent sets of this graph. And then you want to pick out which independent set has the most nodes. Okay, yeah, so basically maximum independent set is looking for a global maximum. It's looking for globally what is the largest possible independent set. Okay, whereas maximal independent set is looking for a local optimum, because all you need to do for maximal independent set is that you have an independent set, and it's not possible to make this independent set any larger by adding additional nodes. Okay, so this maximal independent set is a locally largest independent set. Okay. But if you compare that to all the possible independent sets, then the maximal independent set might not actually be the globally largest independent set. Okay, yeah. However, maximum independent set, okay, this is a very hard problem to solve. It's NP complete, okay. Whereas maximal independent set, there are very simple algorithms to compute maximal independent sets, okay. And so today we're going to look at how to compute maximal independent sets. Yeah, and then wait. I'm sorry. I did something wrong here. I'm sorry. For this first graph, okay, this is a maximal independent set because I said that you could add this node. Okay, you cannot add this node because then these 2 guys will be connected. Oh, sorry about that. Okay. All right. So then, sorry. Right. So then, the example I would have to give is suppose you Yeah, so suppose you did not include this node. Okay, so suppose currently you have these 8 nodes, and the only so let me just redraw this. Okay, so suppose you have these 8 nodes over here, right? And suppose currently all you have is the single node in your independent set. Okay, then it would not be maximal, right? Because in that case, you could add, for example, this node. Or sorry, not this node. Why do I keep adding? Right, you could add this node, right? Or you could let me erase this. All right, or you could add this node, or you can add a bunch of other nodes and still have an independent set. Okay, yeah. So so this thing over here is not an MIS. Okay, however, this thing is MIS. Okay, sorry about that. Yeah. Okay, so anyways, what we're trying to do is to find an MIS. Okay, so in fact, any of these 6 graphs would be okay, would be an okay solution for our problem. Okay, however, you can see that even though all of these graphs are maximal independent sets, only this one and this one are actually maximum independent sets. Okay, because the other ones only have 2 nodes, and the maximum independent set has 4 nodes. Okay, all right, so I'm not going to get through too much of this, I guess, but let me try to finish up this slide, okay, and then we'll do the rest next time. Okay, so yeah, so first of all, why would we care about maximal independent sets, right? What is like an application for maximal independent sets? Well, one application would be, suppose, so here, these 3 red nodes are independent from each other, okay? And so that means that they're not connected to each other. And suppose these edges actually represent some sort of interference between nodes. Okay, in that case, when you select a bunch of nodes in a network, you don't want to select nodes which can interfere with each other. Okay, so if you select this red node over here, you do not want to also select this node, because that would interfere with each other. Those 2 nodes would interfere. Okay, so the reason you want a maximal independent set is that you want to select as many nodes as possible which do not interfere with each other. Okay, and then maybe these nodes can perform some sort of work, and they can work concurrently at the same time because they do not interfere. Okay, if you select 2 nodes which are connected by an edge, right? So if you, for example, select this node also, right, then this guy interferes, right? So these 2 nodes cannot work concurrently with each other. Okay, so that's one reason why you might want to compute a MIS in a distributed setting. Okay, so now there's actually a very simple algorithm to solve MIS. Okay, so again, MIS is polynomial time solvable, whereas maximum independent set is NP complete. Okay, but for MIS, the way to solve it is all you do is you just take any node, okay, and you add it to your maximal independent set. Okay, but once you take this node, then you're not allowed to also take any of its neighbors. So therefore, you're going to remove all of its neighbors. Okay. And when you remove a neighbor node, you can also remove all of the edges from that node. Okay, and then you just keep repeating that procedure. Okay, yeah. So you just so the algorithm is, again, just pick an arbitrary node and put it into your MIS. Okay, and then take all of the neighbors of that node and just remove them. Do not put them into the MIS. Just take them out of the graph. Okay, and then when you remove these nodes, you also remove all of the edges around these nodes. And then you just keep doing this until your graph becomes empty. Okay, because each time you do this, you make the graph smaller. So then if you keep doing this, eventually your graph becomes empty. Okay. All right, now this is a correct algorithm, but one problem is that this algorithm is going to take a linear time. Okay, so for example, if you have a chain graph like this, right, then if you take out one node at a time, right, then you see that yeah, you're basically going to have to take a linear time in order to finish this algorithm. Okay, and also another problem is that this is a sequential algorithm, right? Because each time you well, first of all, this linear time might look pretty good. Okay, however, because you're in this distributed setting where all of the nodes can work together at each time point, then potentially you can have an algorithm which is faster than linear time, right? Because all the nodes are working together in each round. Okay, so in principle, you could have all the nodes complete the algorithm in just a single round. Okay, whereas the the simple algorithm is going to take a linear number of rounds. Okay, Yeah. And the other problem with this algorithm is that it's sequential, okay? Because whenever you do this, whenever you add a node to the MIS, right, you have to remove all of its neighboring nodes and edges and then repeat, okay? So that means that you cannot have two nodes which add themselves to the MIS at the same time, okay? Because, for example, if you go back to this line graph again, right? So if you add these two nodes at the same time, right? So if you just have all the nodes work completely independently, then these two nodes might try to add themselves to the MIS at the same time, and then now you get an error, right? Because you cannot have both of these nodes in the MIS. Okay, so yeah, so these are the two problems with a simple algorithm. Okay, one is that it's slow, and two is that it's sequential. Okay. So instead, what we want is we want a much faster algorithm, and furthermore, we want this algorithm to be distributed, to not work in a sequential fashion. Okay, right, but I guess unfortunately I am out of time here, so I guess we will have to continue next time. Okay, so next time I'll tell you about what this distributed MIS algorithm is, and then we're going to analyze its time complexity and basically see that it finishes quite quickly. It basically finishes in like logarithmic time, okay, instead of linear time. Okay, any questions about anything? Sent an image. Oh, okay. Oops, where's my mouse? Okay, let's see. How do I open up this image? Oh, okay, all right. Okay, is this reasonable? Same imbalance can lead to different sums of sets. Okay, so for example, yeah, okay, right. You're right. I mean, in both of these two cases, right? So you're giving two sort of groupings where they both have the same imbalance, but the groupings are different from each other. Okay, so I would say that this is reasonable. Okay, because well, it depends on how you want to define your problem, right? But in this problem, suppose our goal is just to minimize the maximum imbalance. Okay, so we don't really care which element is imbalanced, right? So in the first case, right, you have that you have an extra copy of element 3, right? In the second case, you have an extra copy of element 1. Okay. Yeah. So suppose you look at all of the elements as being sort of the same as each other. Okay. So you don't care which element is imbalanced. You just care how much of an element is imbalanced. Okay. In that case, it is reasonable to look at this this measure, this L infinity thing, which I defined. Okay. You could, of course, look at some other problem. Okay. And in that case, you would have to do some other type of analysis. Okay. Yeah.